Today we're going to be looking at logarithms, just like we learned a new number the other day when we learned e. Today we are learning a new function. So let's go ahead and take a look at what this function is all about. Now the function, the logarithmic function actually stems, or at least in my opinion, it kind of stems from this idea. Let's say you inherited $50,000 and you immediately put it in the bank or into the stock market for 10% interest. How long will it take you to become a millionaire? So here's the setup for it. Now this is just our A equals principal times the natural number e raised to the rate as a decimal times time. So there's my rate, 10%, written as a decimal times time. There's my original amount, 50,000, and I want to become a millionaire, so that's the amount I want to end with. So if I were trying to solve this, I'd first undo this multiplication with division here. Oops, 50,000. Let's not start with too much money. And we'll just simplify here, here. So 5 into 100, so 20 equals e to the 0.1t. And so we're trying to find the time. How long will it take us to get to that $1 million? But I have no way now to solve for t. I can't, there's just no way to get to that t. You could try to, I don't know, t root it maybe, but then you'd have the t root of 20 on the left-hand side. We just can't get to it. So there's clearly a problem, and maybe this is unsolvable. Maybe we can't predict the time when you would get to $1 million, but that doesn't seem right if we know how much we're getting paid. So let's first talk about the concept of inverses, okay? It's an inverse problem. In other words, I want to solve for the where normally the x is. Usually equations are solved for y's, but I want to get it so it's solved for that x. And this is related to inverses very closely. So let's look at those real quick. Here's our standard exponential function, y equals b to the x. If I wanted to find the inverse of it, I would flip-flop my x and my y, and then I'd have to, I didn't have to change it to function notation. I guess this should have been a number 2 here. So let me slide it down. There we go. So I exchanged my x and my y, and now I'm supposed to solve for y. That should say solve for y right there. Now I'm supposed to solve for y, but I can't do this, okay? I just have no way to y root both sides. But if you remember, when we were doing inverse, one of the things we asked on our quizzes and tests and things we looked at in class was how do you determine if an inverse has an inverse function? Okay, we can find an inverse, but is it a function? So if we remember that method, it is called the horizontal line test. And that will tell us even if this function here has an inverse. And so I'm going to graph it here for us. Here's the graph of y equals 2 to the x. Okay, it could be y equals e to the x power. It doesn't matter. It's an exponential function. This exponential function will pass the horizontal line test. Any place you draw a line that's horizontal, it only hits it in one point. Even down here, remember it never touches the x-axis. It gets infinitely close to it. So even if you draw a line right on the x-axis, it never quite touches it. It's always going down, down, down. So it passes the vertical line test. And if it passes, that means it must have an inverse function. And in fact, I can use symmetry here. Remember, it's a reflection over the line y equals x. I can actually see what the inverse looks like here in blue. So if f of x is equal to 2 to the x, this blue line represents the f inverse of x. But that's what I couldn't find. In fact, how did I graph it? The way I graphed it is I just exchanged my x and my y in my equation. And I didn't have to solve it for y. These Desmos can still generate points for this. And so it graphed the blue line when it generated after I switched the x and y. So I know this thing exists. And that means this equation should be solvable for y. I should have an equation for this blue line. I can see the blue line, I better have an equation. Well, this is the problem that mathematicians ran into. They knew from theory that this inverse had to exist. They could see the equation for it, they knew what it looked like, they knew how it behaved, but now they needed to figure out some notation to represent that, and that's where the logarithm comes in. So think of it this way. Here we've got 2 to the x, and if we wanted to figure out what x was, maybe we can do that in our head. We know x equals 3. Why? Because 2 to the third, 2 times 2 times 2 is 8. What power gives you 16? Well, if 3 of them multiplied together give you 8, take it times 1 more 2, it must be 2 to the 4th. If we got to get to 32, it's times 1 more 2, it's x to the 5th. So 2 to the 5th power gives you 32. But how the heck can we solve this then? How can we figure out what x is on this 2 to get 4,194,304? And that's what logarithms tell us. Logarithms tell us the exponents on a base that will give you whatever the result is you desire. So here's how logs are defined. And it might be easier to look at it from this standpoint. If we had y equals some b to the power, and I wanted to figure out what x is, the exponent, well, it turns out x is equal to, and this is the notation we use to indicate that I'm looking for the exponent on what? I'm looking for the exponent of an exponential function with a base of b that gives me the value y. So I'm looking for the exponent that can be applied to base b that would give me the solution. Okay, another way to think about this is if f of x is b to the x, the inverse would be log base b of x. And I know that looks like the exponent, but this is the x after we've transposed or exchanged x's and y's. But what this would do, this function, if I plugged in the f of 2, let's make my function f of x equals 2 to the x. If I wanted to find the f of 3, for example, it'd be 2 cubed, which gives me 8. The inverse function would take the 8, so it's log base 2 of 8, and it would convert it back into the initial value I put in. So the function takes 3, maps it to 8. The inverse takes 8, and maps it back to, in this case, 3. This logarithm is saying 2, the base, to what power gives me 8? And the answer is 3. So logarithms tell us exponents. Now this is obviously very confusing at the very beginning, so the first thing we do is we just practice jumping back from these equations in log form into exponential form. Now it really helps, first of all, to make sure we read this right, and I think I had it written down somewhere, but that's all right. This is read, log base 2 of 16 is equal to 4. Now what this means, this is your base. So when your base is 2, remember the logarithm tells us the exponent, so 2 to the 4th power is 16. That's all that says. So log base 2 of 16 is what exponent can go on 2 to give you 16? Well, it's the 4. So 2 to the 4th equals 16. Okay, so your base of your logarithm is your base of your exponential. The exponent is the answer to your logarithm. And the argument of the logarithm is what that base to the exponent equals. Let's get another one here. This says log base 4 of 1 equals 0. That means your base 4 to the exponent of 0 must give you 1. 4 to the 0 power equals 1. So when you're switching these things, the first thing you want to do is identify your base. Your base of the logarithm is the base of your exponential. The answer to your logarithm Logarithms give us exponents, so that's the exponent. And then the argument of your exponent, or your logarithm, is the answer to your exponential. So there's the argument right there. That's what we're taking the log of. And this is a true statement. 12 to the first power does give you 12. Just like our last one, 4 to the 0 power does give you 1. These are all true equivalences. Okay, so let's take a look at converting this one to exponential form. So the base of your logarithm to the exponent. Remember, the exponent is the answer. So I got to raise the whole thing to the -1. So I better put it in parentheses. And that equals my argument here, the logarithm 4. And that's true. The negative exponent means flip this over. So that'd be 4 over 1. So 4 equals 4. Now let's go in the reverse direction. Let's say I have an exponential function and I want to convert it to its logarithmic equivalent. Okay, so I just start by writing the word log, and you'll see me write it in cursive, kind of like that. The base of your exponential is the base of your logarithm, so it's a base 5 logarithm. My argument is the answer there, and the result of the logarithm should be the exponent. So it says the log base 5 of 25 is 2, and all that means is 5 to the second power is 25. We've got a couple more of these left. Let's convert to log form. So we'll just write log. We'll go get our base. Our base is 10. We're taking the base 10 of 0.1, and it is the exponent, -1. Now this right here is our logarithmic form. And if you go to your calculators, we can find a log button on our calculators. So let's go ahead and pull that thing up. Get rid of that right there. And there's my logs. And you can see I've got 2 logarithms on my calculator. If you can see that, it's right over there. I've got a log base 2 and a log base 10. This one is a log base 10, which means our calculator can do this logarithm. So I'm going to take the log base 10 of 0.1, and I will press the log base 10 of it, and you can see it does give me -1. So our calculators do base 10. In fact, if your calculators doesn't look like mine, you may just have a log button. This is called the common logarithm. Okay, and common logarithms are always the same base. They're just base 10. So when your calculator just says log, it is saying log base 10. So you should be able to type in 0.1 on your calculator, hit that log button, and it'll tell you -1 is the answer. Now we didn't need to do that on our calcs because we already had the relationship here. Let's look at our last example. Let's see, our calculator would not do this one. So let's change it to log form. So there's log. What's our base over here? Well, it's a base 8 of what? 4 gives me the exponent, 2/3. So it says 8 to the 2/3 power is 4. Now we could check that really quick and see that that is true, everybody. 8 to the 2/3, the 3 means to cube root the 8, and then the 2 means to square it. Well, the cube root of 8 is 2. 2 squared is 4. So you can see it's true. And that's the logarithmic form of that equation. One more logarithm. Base 6, because that's the base of the exponential, of 1/16 would be equal to -3. And I do not believe that is correct. In fact, I know it's not, because 6 to the -3 is not 1/16. 6 to the -3 is 36 times another 6. 6 carrier. I think it's it's 216 is what that should be. So I'm going to make that correction. 216 is what it should be. That's just a number mistake on my part. Okay, so that's all you have to do today. Google form in the classroom, and you can see, hey, here it is as a logarithm. Change it to exponential form. Remember your